Turbulence-induced 2D correlated image distortion. This is a real video taken on a hot day through turbulent atmosphere. Atmospheric turbulence randomly changes the refractive index along the line of sight. This creates refractive perturbations to light passing through a scene, generating geometric distortions such as these. Our goal in this work is to render turbulence-induced image distortions which are physically accurate. This is a valuable tool in the development of imaging systems and image correction algorithms. Rendering should include these steps. Simulate a kilometer-scale 3D random turbulent field. Ray trace through this 3D refractive medium from a scene point to a millimeter-scale camera aperture. Repeat this process for all points in the field of view to obtain a distorted image. This is computationally complex. We believe that for some applications there is no need for 3D simulation. Image distortion is approximately an operation in 2 dimensions. Previous work in 3D ray tracing to render refractive objects and atmospheric phenomenon is computationally complex. Image simulation in 2D employs empirical parametric models or simple Gaussian random functions to generate distortion fields. However, these 2D methods do not have physically consistent spatial correlations. What affects turbulence-induced image distortions? A camera, having focal length f, observes an object point O at distance L. Without turbulence, the line of sight is straight and an object point O is imaged at pixel p. With turbulence, due to refractive index fluctuations, the light from the same object point arrives at the camera at a random angle of arrival and is imaged at distortion pixel p plus e of p. At the image plane, this is the original pixel p, and e of p is the random distortion vector. Then, according to theory, the variance of the angle of arrival is proportional to the product of turbulence strength, distance, and camera aperture. What happens if we have another object point? Turbulence causes each of these lines of sight to deviate by random angles of arrival. At the image plane, these are 2 pixels separated by a vector v. The magnitude and direction of distortion at each point depends on the distortion of its neighbors. This interpoint correlation is non-trivial. There is a correlation between the angles of arrival of O and O'. These lines form a plane pi. The correlation depends on the directions of these angles of arrival relative to this plane. Let us define 2 terms. Suppose an angle of arrival perturbation is within the plane pi. Then this perturbation is termed parallel. Angle of arrival perturbation is perpendicular if it is perpendicular to this plane pi. In the image plane, these are the perpendicular and parallel distortion projections. In general, the distortion has both parallel and perpendicular components. An expression for the correlation b of theta for both parallel and perpendicular components was theoretically derived and can be computed as shown in this plot. See the paper for details. Note that for a fixed point O, the parallel and perpendicular axes and components are defined depending on another point O'. In reality, we have multiple object points and thus a non-trivial correlation between multiple pixels. Our goal is to find a distortion field with physically accurate variance and correlation. Thus, we are dealing with a non-trivial field. This segment from the good, the bad, and the ugly demonstrates the kind of directional interdependence we are dealing with. This is a truel, a duel among 3 opponents. Their decisions and the directions they point to are interdependent. The decision of each opponent to point the gun in a certain direction is affected by the other opponents. This is directional interdependence. Let us first see how to create a random correlated scalar field. Suppose we have 2D white noise. To obtain a correlated scalar field, we need to convolve it with a 2D kernel such as this. This kernel is directly related to the correlation function c, which is a function of the pixel separation v. This is a correlated scalar field. This generalizes to vector fields. To create a correlated vector field, we need to convolve a white noise vector field with a matrix-valued kernel. Here again, this matrix-valued kernel is directly related to a matrix-valued covariance function. We wish to find a correlation function c such that the induced parallel and perpendicular autocorrelation functions match the theoretical b. Let's look at the matrix-valued correlation function in more detail. The image plane contains some random pixels. Consider these 2 pixels with separation v1. Since the correlation depends on the relative position of the pixels, we plot the vector v1 centered at the origin. The distortion vectors are random and correlated, so they have a correlation matrix of size 2 by 2. Each pixel pair has its own correlation matrix. Now let us look at each component of the correlation matrix. There are 4 components. Each component depends on the relative separation v. The components of v1 are mapped here. The components of v2 are mapped here. The components of v3 are mapped here. Finally, we get a matrix-valued function. Now recall that random distortion vectors have both parallel and perpendicular projections. In the paper, we show that this form of correlation function fulfills all the required properties, and the theoretic correlations B are used here. Based on this formula and the theoretic correlations, we compute the matrix-valued correlation function. Now we create a random distortion field, E of P, whose autocorrelation is consistent with C of V. Recall that the correlation distortion field is obtained by convolving the white noise field with a matrix-valued kernel, which is directly related to the matrix-valued correlation function. This convolution is the relation between the correlation function and our required kernel. This can be solved in the Fourier domain. While there are many 2 by 2 matrices K satisfying this relationship, it is natural to choose the symmetric square root of C of omega. Given C of omega, its matrix square root can be computed per omega using this formula. Our theoretical recipe is the following. Given camera and turbulence parameters, compute the theoretical correlations B. Then compute the matrix-valued correlation. Perform a Fourier transform of the correlation function. Take the square root to obtain the matrix-valued kernel in the Fourier domain. Sample a Gaussian white noise vector field. Apply the Fourier transform to the noise field and multiply with the kernel to get the Fourier transform of the distortion field. Apply the inverse Fourier transform to obtain the distortion vector field, which has unit variance. Using the camera and turbulence parameters, compute the correct variance of the angle of arrival. Amplify the distortion field to adjust the variance. We render the distorted image by warping it according to the obtained distortion vector field. Here are some examples. Finally, we empirically verify that our distortion statistics are consistent with the theory. Let us choose a random subset of 100 pixels. We then generate 1500 distortion fields, where each one is based on a different sampled white noise field. Then we compute the correlations for different pixel pairs and compare to the theory. There is very good consistency between the theoretical angle of arrival correlation and our rendered fields. In this work, we focused on a particular turbulence-induced image effect, distortion in a 2D image. This may be extended to express other turbulence-induced image effects, such as blur and scintillation, which are both random correlated fields and have closed-form physical models. Turbulence is actually dynamic, and so are its image effects. The 2D distortion field is correlated both in space and time. To render videos, this spatial-temporal correlation should be simulated correctly. In some cases, the turbulence field is not spatially stationary, specifically for oblique views such as in astronomy. Extending the approach to such cases is also important. To summarize, in this work, we show how to render image distortions consistent with turbulence theory. We bypass 3D numerical calculations and ray tracing by performing only 2D operations. We create a 2D random distortion vector field with non-trivial correlations. The correlation function depends on the relative orientations of all object pairs.